All right, now we're going to talk about ionization energy. And ionization energy, the focus of ionization energy is a way to talk about how much energy it takes to create an ion by yanking an electron off of it. Okay, now the properties of an atom are very much determined by how much energy it takes to yank off an electron. And that's something that we just need to discuss because it's a big deal and it changes how things behave and how things interact with one another. Okay. Now, the definition of the ionization energy of an atom or an ion is the amount of energy needed to remove an electron from an atom or an ion in the gas phase. Okay, so the question that I had when I first learned this is, why in the gas phase? Why does it have to be in the gas phase? And the simple response to it is by putting them all in the same phase, it takes away the amount of energy it takes to change phase. We already talked about our thermodynamics, and we talked about the fact that we have to input energy to take a solid and change it into a liquid, and we have to put more energy in to take a liquid and change it into a gas. And so by having to put everything in the gas phase, we've leveled the playing field, and we can actually compare the ionization energies of elements or ions in a meaningful way. Because if we didn't do that, the numbers would be utterly meaningless when we started talking about changing phase or bringing all that stuff up. And so that's why that's the case. Now, when we're talking about ionization energy, we can measure it for the amount of energy it takes to pull off a first electron. That's the first ionization energy. That's right there. We can take off and measure the amount of energy it takes to pull off the second electron. That's the second ionization energy right there, and so on. We can go all the way out to the third or the fourth or the fifth or the sixth electron if we wanted to do that. And in fact, as it turns out, that has been done. Scientists have done those numbers and figured out those calculations. And the biggest impact, the biggest thing that we've learned is as you pull off more and more and more and more and more electrons, well, it requires a significant amount of energy to do that. And so the more electrons we're trying to yank off an atom, the more energy it takes each and every time to pull that electron away. And again, if we think about it, it makes sense. And so what I have here is a table showing the ionization energy of pulling off a second electron or a third electron. So if we look at sodium right here, sodium pulls about 486 kilojoules, I believe is the number. It pulls kilojoules per mole to yank off for 96. Sorry, couldn't read it. 496 kilojoules of energy per mole to yank off that first electron. But then to yank off that second electron off a sodium atom, well, that's 4,562 kilojoules of energy per mole. Now, in sodium, in the case here, we're looking at one electron. That's a valence level electron. Now we get here, now we have one fewer electrons than protons, and we're talking incredible amounts of energy to yank off that second electron. It's a huge quantity because that's the core number of, that's in the core of electrons for a sodium atom. And the trend continues. If we look at magnesium, magnesium is a +2 ion most of the time. Takes 700 some kilojoules of energy per mole. The second electron is 1400 kilojoules. So it's almost double the first one. Now, this happens in nature pretty readily. We see magnesium 2+ ions all over the place. We don't see magnesium 3+ ions very readily. And that's because by the time we make this step up here, it's 7,000 some kilojoules of energy per mole. That's an exorbitant amount of energy. And so we see the trend carry through here. And so this grayed out section is the amount of energy it takes to get into the inner shell electrons after we're pulling off the valence electrons. Now, what we're looking at or what we're thinking about is the amount of energy to yank them off. And so we can do that. We know that ionization energy 1 is always going to be less than ionization energy 2, is always going to be less than ionization energy 3, and so on and so on. And so if we look at this data, in argon, this data shows that we went all the way to the 7th electron. 1, 2, 3, 4, 5, 6, 7. And you can see 1,500 some kilojoules per mole. We went to 2,600 some kilojoules per mole. We went to 3,900 some kilojoules per mole. 5,000, almost 6,000 kilojoules per mole. Now we're up to 7,200 kilojoules per mole. 8,000, and here we're at 12,000 kilojoules per mole to pull that electron off. And so it's always safe to say that we're going to have more energy required to pull off the second and third and fourth and fifth electrons. It just takes more energy because the protons stay the same and there's fewer electrons on the outside, so those protons can pull in really, really tight and they can make you work pretty hard to yank them off and have to expel more energy. And that's what's going on here, is those. So now, so it's easy to see how the energy to remove electrons is rapidly increasing when you begin removing nonvalence electrons, and that's the grade section. We already talked about that, so we're good. Now, what are the trends in the periodic table with first ionization energies? Well, ionization energy 1 generally increases as we move from right to left in a periodic table, in a period on the periodic table. So if we start over here, we work our way that way. Generally speaking, the ionization energy increases as we move on over. And that makes sense because we know that metals very easily give away their electrons to react. And we know that metals form positive ions all the time. And so it makes sense that the things that would give away electrons most readily would have the lowest ionization energy. And that's where metals are located over here on your friend and mine, the Ultimate Party Cleaning Guide, the periodic table. And so, now there are irregularities. Of course there are irregularities, but that's the general trend. So, and why? Well, because I just said the metals willingly give up their electrons. Non-metals are more electronegative, and they don't give away their electrons very well at all. So that's that. In general, your ionization energy generally decreases as we go down a column. So as we move down any column, our ionization energy is decreasing moving down. And that's going to be due again because of the increased valence level. So all the core electrons get bigger as we go down, and they get further away. And because they're getting bigger and the valence electrons are getting further and further and further away from the nucleus, they lose a little bit of their pull back in, and so it's a little easier to yank them off. Okay. Again, that stands to reason when we talk about the fact that the most active metal on the periodic table is going to be way down here. And so it's further away, and it's the most active because it's the least amount of energy to yank off an electron from it. So that's why it's the most active. So now, usually, smaller atoms have higher ionization energies. Now again, the same factors that impact atomic size are at play here with ionization energy. So the amount of energy needed to remove an electron is dependent upon the effective nuclear charge, the ZEF, and the average distance of the electron from the nucleus. Now, the slight irregularities that we witness in the first ionization energy are going to be due to the energetics of having paired electrons in different orbitals. And so nitrogen has a higher ionization energy than oxygen does. Well, it's due to the electron repulsions that exist in an oxygen atom due to having 4 electrons that are paired in 2 orbitals, while nitrogen only has 2 electrons that are paired together in one of the suborbitals in a p. And so because we've got more electrons jammed into the smaller space, 2 suborbitals, oxygen is readily willing to give away electrons more so than a nitrogen atom is. And so that's where that all comes from, is because we have different energy effects of having more electrons paired or unpaired floating around in the p orbitals, or what other orbital. So there we go.